It says use spherical coordinates to evaluate the triple integral. So we got triple integral over q x dv. We're going to use spherical coordinates where q lies between two spheres, x squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 9 in the first octant. Here's what I'm going to do on this one. I'm going to draw my 3D picture in 2D. In other words, I'm going to look at a cross-section of it because they're spheres. They're symmetrical, right? So, you know, I'll do it this way. So here's my x, y, and z axes. So we know what the sphere x squared plus y squared plus z squared equals 4 looks like, right? Center at the origin, what's the radius? 2. So I'm not gonna draw the entire sphere. I'm just gonna draw maybe a cross section in the YZ plane. Oh, is it? Okay. I guess I should read my problems that I actually write. So good. I won't draw the whole thing. I'll just draw this cross section here. And you could imagine, you know, it also has a cross section here, and you can imagine what it looks like. But it just gets messy if you draw all that. And then what about a cross section of x squared plus y squared plus z squared equals 9? What's the radius there? 3. So, I mean, you can't usually do this. You can't usually get away with doing this, but what I'm trying to say is the region we're looking at, Q, is in between those two spheres, right? And because we have such symmetry here, I think that gives me as much information as I need in order to find what's ultimately going to turn out to be rho. Because if we're in the first octant, I think we're going to, it's pretty darn easy to figure out what the two angles are, right? So let's set up kind of a template integral. Yes. So what's the volume element? Phi, phi, fo, fum, right? It doesn't matter. I usually use d rho, d phi, d theta. But it really doesn't matter if you reverse d phi, d theta. It doesn't matter. Even d rho. Usually they're constant, so it usually doesn't matter. And then, there is an integrand here. What is that? X in spherical coordinates. Sine phi, sine theta. Cosine theta, there you go. That sounds better. I was just writing down what you said. All right. I'm at the point where I'll just write down what you say, so say the right thing. Okay, so what does rho lie between? Well, what I'm trying to say here is this picture is enough. I know rho, I'm going to draw this dotted because this is not part of that length, is it? Rho lies from here to here radially. So from 2 to 3. Now, if phi is, if our q is in the first octant, what does phi have to range between? 0 and pi halves? What about theta? 0 and pi halves. So let's clean this up. Limits of integration won't change. And then we have rho to what power? Rho cubed, and then sine squared phi, and then cosine theta. Did I miss anything? D rho, d phi, d theta, and then somebody said, split it up, and I think that's a good suggestion. Okay, so integral 0 to pi over 2. I'm looking at the outer integral. That's with respect to theta. So what goes inside? Cosine theta, d theta. Integral 0 to pi over 2, that's the middle one with respect to phi. So what goes in there? Oh, there's your power reducing identity, or the need for it. And then the integral with respect to rho, 2 to 3 rho cubed, d rho. Everybody believe that? It's the integral of cosine Sine evaluated from 0 to pi halves. I'm gonna evaluate these in, well, I guess I can't do them in parallel. There's an extra step in here, isn't there? All right, I'm gonna pull out the 1/2. Don't tell anybody where that came from. No. See if you can figure out where that 1/2 comes from. It's not from evaluating an integral. Okay, it's magic, yes. So what should go in here if I pull the 1/2 out? 1 minus cosine of 2 phi. Does everybody see where the factor of 1/2 comes from? Normally you put that 1 minus cosine of 2 phi, that's a power reducing identity. You put that over 2, right? That's what sine squared phi is equal to. But instead of putting over 2, I bring the 1/2 out front, make life easy. And then we can't evaluate this integral right now. What do you want to call that? Well, first of all, what can we bring out in front if we evaluate it? 1/4 rho to the 4th, evaluated from 2 to 4. 2 to 3. I don't know what's wrong with me. It's time for me to go home. There we go. I'm just seeing if you're awake. Yeah, that's it. All right, so what do we get out in front? 1/8. We get a 1/8 out in front. Okay, sine of plug in pi over 2, what's that? That's 1, right? Minus sine of 0. That's 0, so that whole thing is just 1. I'm not even going to write it down. Will you be offended if I don't write that down? No, okay, good. And then integrate this guy for me.
Theta minus 1/2.
Not, well, phi, right? Phi, and then what do you get?
Minus 1/2
Minus 1/2 sine
sine.
of 2 phi. And then 0 to pi halves, right? And then what do we get? When we plug in the upper limit, what's 3 to the 4th?
That's 81.
81 minus 2 to the 4th? 16, yeah. All right. All right, so what does this turn out to be? 1/8, pi halves, and then what? Okay, when we plug in pi halves, we end up taking the sine of pi, which is 0. So I'm just going to put a minus 0 there as kind of a placeholder. Minus, does everything 0 out? Yeah, when you plug in 0, both 2 times 0, 0, sine of 0, 0. Okay, so everything zeroes out there. What's 81 minus 16? 65. Oh my gosh, it's not too bad. So what do we get? 65 pi over 16. I've seen worse.